Aloha, everybody. This is Gigi from Kauai Community College. In this video, we will be talking about volume of solids, and we would do this by slicing. All right, so let's get started. So the idea is if you want to find the volume of this golden looking solid shape right here, what we are going to do is we're going to start with slicing into small little slices, right? And we are going to find the volume of each one of those slices, and then we're going to add them all up. Okay, so let's just consider that one slice, for example. We first need to know the area of the base, because volume of a straight up solid is the area of the base multiplied by how thick, and how thick would be delta x, right? So then the volume of one slice is going to be A of x, which is the area, multiplied by delta x. Now, if we were to sum up n slices, we would use the notation of sigma, right? The sigma notation is for sum from n to k of the area multiplied by delta x. And then the idea is if we let these slices getting thinner and thinner, or there would be more and more of those slices, or we would say let n goes to infinity, right? Infinitely many of those slices, then our estimate would be very, very close to the volume of this shape, close enough for us to be happy and say, oh, that really is the volume of that shape, right? So when we say let n goes to infinity, that's the idea of limit. And when we take the limit of the Riemann sum, that becomes the integral. Okay, and that's the idea. So just to summarize what all of that mumbo jumbo I just said is, in order to find the volume of a shape, we are going to add up infinitely many slices to get the total volume as an integral. And the integral is from A to B of the area with respect to x. Right now, add if you have vertical slices, but if you have horizontal slices, then instead of dx, we would have dy, but the concept would be the same. Okay, so let's take a look at some particular examples. Example number one, suppose the region is between the curve y equals y equals square root of x, the vertical line x equal to 3, and the x-axis. Okay, so visualize that, that area. That would be that right there, right? And that square root of x is the red, the blue is x equal to 3, and then you have also being bounded by the x-axis, which is right there. And then we are going to revolve it about the x-axis. So I'm going to copy that reflection on the other side, revolve it so you'll get a three-dimensional shape, and that looks like that bell shape right there, right? Now, what are we doing here to find the area by slicing? We are going to slice it into smaller slices like this, right? So suppose I am going to put one particular slice up and blow that up so that we can see. The thickness is defined as delta x, okay? And the one slice would look like this, where the cross section is a circle, right? So with the circle, you'll need to know the radius in order to find the area, and then you would multiply that by how thick to find the volume. So where does the area comes from? Right there. And that extended from the x-axis to the red curve. So that is defined as square root of x sub k for that particular k slice. And then the area would be pi r squared. Okay, so square under square root, you have pi times x sub k for that one particular slice. And then we would say the thickness of that slice is delta x, so that the volume of that one particular slice would be pi times x times delta x. Okay, and then we are going to do what with this? How many slices are there? There are n number of slices in this shape. So sum that up from k equal to 1 to n of pi x multiplied by delta x. And then we would say let n be bigger and bigger and bigger. That means take the volume as n goes to infinity. And when we do that, that defines an integral. Okay, and what is that integral? It would go from 0 to 3 right here, 0 to 3, 0 to 3 of pi x dx. So this would be the area, and that would be how thick, right? The area times how thick is the volume. Okay, and when you integrate that, you'll get pi x squared over 2, evaluating it from 0 to 3, plug in the numbers, you have 3 squared is 9. So that must be 9 pi over 2. And then when you plug in 0, that's 0. Therefore, the total volume is 9 pi over 2. And that is how slicing works. Okay, let's take a look at another example where the cross section will look just a little bit different than this one. Okay. For example, the volume of find the volume of a solid that is generated by revolving the region bounded by the y-axis. So visualize that region, y-axis, square root of x, and then 2 minus x. Okay, when I put up the graph, it looks like this. And the region is this part right here that looks like a triangular part right there by the y-axis. And we are going to revolve it around the x-axis. So I am going to copy the other side and say that's the solid that I'm looking at. What's going on here? How does the cross section look like? And if you say it looks kind of like a donut shape, you're right. Okay, let's see here, because we have to take out the hollow part. We would need to consider the big radius, which is the blue, and that is 2 minus x. And then the smaller radius that came from the red, which would be square root of x. So then the area of that cross section is area of the big circle minus area of the small circle. Okay, and that would be that. When you substitute that in, clean that up, you get that. So then the volume, as we see earlier, I'm not going to do the summation. You get the idea, right? You add up a bunch of volumes and then take the limit as n goes to infinity, and that should give you an integral from a to b of the area dx. So here, volume would be from 0 to wherever that intersection is. And if you go and solve for that intersection, it's at 1, 1. So we're looking at the integral from 0 to 1. Okay, the integral from 0 to 1 of the area dx, a of x dx. Okay, and then go ahead and take the integral. You'll get something like that. And we are evaluated from 0 to 1, right? When you plug in the values and do the calculations, you get 17 over 6 pi. And that is the volume of that shape. Okay, that is it for today. The next example, the next couple of videos, we'll do things in more detail, and maybe we'll have a cross section that goes horizontally. So we'll deal with dy instead of dx. Okay, that's it for today.